Hello, good afternoon. My name is Sebastian Echeverria, and I'm the principal investigator for the High Assurance Software-Defined IoT Security Project, also known as Kalki. The context of this project is also looking into the future. We realize that the DoD will have an increasingly high need to integrate commodity IoT devices into their networks. However, there's a security concern there about trying to use potentially untrusted devices and connecting it to secure systems or networks. The goal of our project is to provide a solution for that so that it's possible to integrate these types of devices into secure systems, protecting both the device and the network they're connected to. It's very easy if you look at the news for the last couple of years. You can see more and more attacks are being carried out against IoT devices, from things like breaching networks to taking over devices in order to create botnets, and even to have potential attacks on the power grid. IoT devices are more and more prevalent, and they are being connected to more and more critical networks. However, since they can sometimes be not very highly secured, and since they can be not patched for long amounts of times, they are a very tempting target for bad actors. So how can we help in trying to use IoT devices if they are so unsecure? There are different scenarios where the DoD may want to use this type of commodity IoT devices. For example, in military bases, they may want to add IoT devices in order to modernize the infrastructure that they have there, to better monitor the base, to control more things around it, and so forth. Or even looking into a scenario like forward operating bases outside of the US, where the flexibility and speed of using commodity IoT devices is a plus. There's also the fact that that's going to be a very hostile environment, where it's very likely that any of these type of sensors that are going to be connected to a network will likely be attacked both physically and through cyber means. And if an attacker is able to find a vulnerability and compromise a device, be it remotely or physically, it can start by reducing the availability of the device and generating fake data, and even compromising the network itself. And even if you have a secure perimeter and everything, if an IoT device is compromised at some point during the supply chain, and so it has, for example, malware installed at some point during its manufacturing time, you can end up with similar results. So if we assume that we cannot control, or that we want to use devices for which we cannot really modify how they work inside, how can we help with this? The solution that we are proposing is to move the enforcement of the security properties to the network and to create a platform that sits between these IoT devices and the rest of the network they're connected to, and allows both the devices and the network to be protected, even if the devices are not fully trusted. The nickname that we have for this project is Kalki, which is a Sanskrit word that refers to an avatar that is the destroyer of filth and the bringer of trust, which is what we're trying to achieve with this solution. So there are two main things that we have to take into account when designing this type of system. One thing is that most solutions that try to add security to a network tend to be not very specific to devices and not very flexible. They tend to have approaches having more generic policies. So when you're trying to protect IoT devices which may have specific vulnerabilities, and you use a more generic system, you may end up either underprotecting for that specific device or overprotecting to try to cover everything. Also, most existing systems do not really allow you to have different policies or different behaviors depending on the threat level that's currently perceived for a specific device. And that's something that we will want to take into account when protecting our systems for potentially untrusted IoT devices. And the second thing that it's important to take into account is that since we are adding this component that's going to be critical in the protection of both the IoT devices and the network they're connected to, we need to have a way to ensure that it's not going to be compromised itself, because otherwise we lose all of the benefits that we're trying to add. So let's talk first about the software-defined aspect of the system. What we're doing here is that we're going to be using software-defined networking and network function virtualization in order to create a platform that's highly dynamic, and it can react to different threat level of threats that are discovered in the environment where this system is working. So we start by adding a gateway in between a set of IoT devices that we have on the DoD network that they want to connect to, which are coding the data node, through which all the traffic is going to be channeled through. We also add a control node, which is going to be both monitoring the devices themselves and controlling the behavior of this gateway that we just added. So since these are IoT devices, each of these devices is going to be sensing and or controlling a set of variables and actuators. And not only, they're going to be used by whomever needs to access those sensors and actuators, but in our system, the control node is also going to be constantly pulling information from those devices to see what they are seeing and to know what they know. Now, all the traffic that's coming to and from the IoT devices is going to be channeled through something we call the micro boxes, which are small chains of containers that are sitting inside the gateway and that can contain any sort of network functionality, network defense, or network monitoring system that you want for that particular device. The concept of micro boxes was developed by Dr. Via Sekar from CMU's Scilab, who is collaborating with us in this project. And the result of these micro boxes, they can have whatever network functionality you want, but they can also send alerts to the control node in case they identify that something strange or abnormal is going on. So the controller is going to be maintaining a state space composed of the data it's pulling from the IoT devices, as well as a security state that it maintains for each of the devices separately. So each device could be in, for example, normal, suspicious, or under attack state according to the data that the control node has. So whenever the controller decides that something strange is going on, it can react accordingly. How would this work? We have a set of policies that are defined in the control node itself, which use as an input the information that the controller is pulling from the devices, the state level that they currently are in, plus any alerts that can come from the gateway. So whenever there's a rule in that policy that triggers a security state change on the system, new micro boxes are going to be deployed and new security measures can be used. For example, if an IoT device that we are monitoring starts providing temperature values that are outside of a certain range that we know is the expected range, a rule in that policy can trigger change in the micro boxes that are protecting that device, and we can start, for example, blocking our traffic to that device until we figure out what's going on. Or if we get an alert from a micro box that's telling us that there's abnormal traffic coming to or from a device, we can also change the security state and deploy micro boxes that are going to be logging more information or analyzing it in more detail or notifying someone to check out what's going on. Since we are both looking at the network traffic and information from the IoT devices themselves, we can try to find attacks that are both physical or cyber, or a combination of both. And also, since IoT devices tend to be much more simple in the terms of the states, APIs, and behaviors that they have, it's easier to try to define some specific micro boxes that protect for specific vulnerabilities for these devices that it can be for more generic devices. So on the other hand, we have the high assurance aspect of the name of the project, which is where we want to be able to ensure certain security properties on these two nodes that we added in order to ensure that our system cannot be compromised and therefore invalidating all of our protections. For that, we are using a platform called UberSpark, which was developed by Dr. Amit Vasudevan, who is part of our project at the SCI, which is a framework for building secure software stacks that allow you to have verified components that can be incrementally added on top of each other. The kind of things that we would like to use this framework for would be to ensure that properties like the policy data integrity on the control node is maintained so that an attacker cannot really change the rules that we're using to trigger the different security states, or the micro box images themselves that are on the data node, as well as all the traffic that is being routed through the micro box images themselves. Kalki is a 3-year project. We just finished the second year. During the first year, going quickly over the things we did, we mostly focused on creating an initial threat model to guide our development. We created a flexible policy model in order to handle all of these rules and reactions. We created an initial architecture and prototype of the system, and we developed some low-level primitives, funky views in this case, in order to ensure the memory isolation that we need to secure the security properties that we just mentioned. Now, in the second year that just finished, I'm going to go in a bit more detail about what we did. We were able to create a full prototype version of the platform with an updated dashboard. We selected 4 representative IoT devices and created policies and micro-boxes to test them out in our system and see how they actually behaved. We ran several experiments and tests to measure the performance and the behavior of the system. And we created an extension to the überXMHF microhypervisor, which we're going to be using, which uses UberSpark, and which we're going to be using to protect the nodes in our system. So in a bit more detail, we finished a first version of the prototype that has all of the functionality that we described in our previous slides. The only part that is not yet integrated is the assurance of the different security properties, which is our next step. This current prototype uses OpenFlow and OVS in order to have the software-defined networking needed to route traffic through the different micro-boxes, which are implemented as virtual machines that can contain whatever network functionality you need. It also is able to monitor device-specific vulnerabilities, different micro-boxes with different behaviors for each device, and is also able to have different policies for each state, for each device, so that a device in a lower threat state can have less protections if they are needed to have more performance. Our current prototype is running on commodity hardware and software just to test it out. Right now, it's a couple of Dell servers with Ubuntu Linux on it. As part of this updated prototype, we designed a dashboard which allows administrators to have real-time monitoring of the system to see the different alerts and the different security states and whatever strange behaviors can be going on inside the system. And it also allows an easy configuration of most of the policies that are defining the root state changes of the system so that an administrator can tweak this as required. In order to test how our system worked, we selected 4 IoT devices, which are smart home devices because those were the easiest ones to try out from the perspective of trying commodity devices, but are representative of different types of sensors, of real-time sensors, analytic sensors, or sensors that are also actuators at the same time. So in order to do this, we defined certain policies that made sense for these devices after looking for vulnerabilities and their behaviors, and created some micro-boxes with different functionality, which could be specific for these devices in order to test them out. So for example, we designed a micro-box that is able to detect brute force attacks that only make sense for the temperature sensor because of the way the temperature sensor works. And we created another micro-box that adds an authentication proxy in between in order to add a layer of security for the IP camera, which doesn't have any sort of authentication built in. In order to test how the prototype and these policies were working, we ran a set of experiments and test case scenarios, which actually we just finished last week, in order to test different aspects of the system. On one hand, we wanted to measure resiliency to attacks, which basically was trying to see if the attacks we were trying to detect and react to were being properly handled by the system. And with the help of our member from CERT, we were able to run several different attack scenarios, and we were able to handle all of the attacks that we were expecting, and even a few more that we weren't expecting as well. In terms of performance, what we wanted to measure was how quickly the system could react to threats and actually change all of its security measures in order to move to the next state. And for the most part, our experiments show that the response time is very quick, on the order of milliseconds, except for one part of the system which we knew we would have to work on, which is the starting up of the virtual machines that contain the micro-boxes, which was on the order of seconds. But it's something that we're going to be working on the next year, and I'm going to discuss it in a bit. And the third thing that we wanted to try out was the scalability, to see how many devices this version of the system could handle. And our results show that the system was able to handle 25 devices connected at the same time without any noticeable issues in terms of performance. The other part that we worked on this year was on the überXMHF verified microhypervisor. This hypervisor is based on the Uber Spark platform that I just mentioned. And the idea is that this hypervisor is going to be sitting between our components and the hardware resources of each of the control and data node, like memory. And it's going to be acting as a gatekeeper that will only allow actually authorized components to access the underlying memory sections. And that will allow us to isolate memory spaces so that only authorized components can access the memory spaces with things like the state machines, which are part of the policies that define how to move from one state to another. This is enforced at compilation time, so only authorized components can actually later at runtime access these memory spaces, and unauthorized components cannot. In terms of next steps, what we're going to be doing in this third year, there are mainly two tasks that we're going to be working on. The first one is to finish the platform, specifically integrate what I just mentioned, this microhypervisor into the rest of the system to ensure that the security properties are being maintained. We will also work on simplifying the integration of new device types, because we realized that some of the steps needed to integrate them into the platform were a bit too complicated or needed too much manual work. And we're going to be working on increasing performance of the system, specifically on what we discussed, for example, in relation with the reaction time for the virtual machines. We're going to be trying using Docker containers, and we have a few other ideas that we want to implement and test out, along with some experiments to test that this is actually working. And the second part that we're going to be focusing on is related to transition activities, finding partners for validating our system in more realistic scenarios, and eventually for transitioning them to existing deployments. We are already working with both Lieutenant Commander Christopher Luken from the Navy and Jeff Greenwald from the Marine Corps to try to identify organizations where we could do this. And we would also like to try to see if we can contact organizations that are already working with IoT projects like the US Army Research Office or Purdue University, so to see if we could have collaborations with them and potentially test our systems with realistic scenarios or deployments with IoT devices. So looking further ahead, by the end of this third and last year of the project, we would expect to have the platform fully tested and working and tried out with realistic IoT deployments, plus our results on this work published. In a couple of years, we should be able to have the platform already adapted to a specific DoD networks where it makes sense and integrated into them. And looking further ahead, some other things that could be easily, or not easily, but could be done, are related mostly to machine learning, to add things, capabilities like micro-boxes that are able to detect abnormal traffic and are able to adapt more to learn and adapt to potential attacks. And use also similar techniques to try to adapt the different policies that are manually defined in the system in order to learn what's going on and be able to react better to those kind of things. So to summarize, the Kalki IoT security platform allows the integration of IoT devices into DoD networks even if they are not really fully trusted. It has flexible policies to define the different states, transitions, and so forth. It can react to both cyber and physical attacks using the information that it's monitoring. It can have different network defenses for each device and for each state, for security state for each device. It can adapt to device-specific vulnerabilities if needed, and it secures critical areas of the system using the Uber Spark framework. This is our team. We're collaborating with CMU's Scilab, and we welcome your question. Thank you very much.
Questions?
You mentioned überXMHF. Verified microhypervisor. Mm-hmm. Is it verified or verifiable at this moment?
It's verified. We have Dr. Amit Vasudeva here, who is the one that's developing that hypervisor.
x86 package of überXMHF commonly verified and find out how it functions. We are working on verifying the ARM package.
And the way it uses the Uber Spark framework, it allows you to basically add functionalities and verify it functionality as you add it, so you don't have to verify the whole thing at once. So the things that we're working on right now to add to the microhypervisor should be easily verifiable as well as we add them.
Have you looked at the DARPA program leveraging the analog domain for security? Well, they have performers, PFP and Red Balloon Security, and you probably want to take advantage of the kind of techniques they're using to look at the associated signatures that are emerging as code execute.
Yeah, we've heard about that, but we haven't really looked in depth into that. That's one of the things that we want to start looking into this upcoming year. I agree. Thank you.
Oh, sorry, Matt.
Have you guys looked into working with some like more, I guess, commodity like vehicle networks such as like Victory standards and such, like porting this functionality to those?
So, I'm sorry, can you repeat the question?
Are you guys familiar with like the Victory vehicle bus? Oh, I guess it will. Yeah, vehicle bus standard.
Yeah.
Have you guys ported to those networks or looked into that?
So yeah, that's not a scenario that we have explicitly tried to address in this case. We tried to start with a more generic approach of the type of network that we were interacting with. That being said, the concepts that we are applying here should also be applicable to those types of networks. We haven't looked explicitly at the differences on how we would adapt it to that type of network, but the main goal of, or one of the goals of this year, upcoming year, is to see how this more generic platform could be adapted to actual networks where it could be used. So that's one of the other things that we could be tackling this year as well.
Anyone else?
Thank you.